Kirchhoff's law has the power to make the circuit analysis of even complex circuits easy.
Whoa! I would like to hear more about it, teacher.
Awesome. Let's begin. Kirchhoff's law was named after a German physicist, Gustav Robert Kirchhoff.
Oh, the law was again named after a scientist.
Well, it's nothing to be surprised about. Happens all the time in physics. Anyway, there are two fundamental laws of electricity discovered by him which are famously referred to as Kirchhoff's law. So first, let's discuss Kirchhoff's first law, also known as Kirchhoff's current or junction law.
Sure. Isn't junction the point where two or more conductors are connected with each other?
Exactly. We call it a junction law because it is applicable in a junction only.
Must be something related to the current in the junction. So, what's the statement, teacher?
You are almost right. Kirchhoff's current law states that the sum of currents entering any junction of a circuit should always be equal to the sum of the currents leaving the same junction.
Hold on, that was too much information in one go.
Don't worry about it. You will surely get the grasp of it. To make things easier, let's have a look at this circuit diagram.
My goodness, there are so many currents. I have no idea what to do with them.
Patience, young one, patience. I'm here to guide you.
All right.
Good. Now that you have calmed down, what's the sum of the currents entering the junction?
Let me give it a try. Looking at their directions, currents I1, I2 and I3 are definitely heading towards the junction. So I guess the sum of currents entering the junction should be I1 plus I2 plus I3.
That's right. Similarly, can you tell us the sum of currents leaving the same junction?
That's easy. That should definitely be I4 plus I5.
Cool. So, all in all, what Kirchhoff's current law says is both the currents entering and leaving a junction should always be equal. Therefore, in our case, I1 plus I2 plus I3 should be equal to I4 plus I5.
Hang on, I think I'm getting it now. This law must be the reason why we get a current of 5 amperes when two wires carrying a current of 2 and 3 amperes respectively are joined together. Am I right?
Absolutely. Also, do remember that Kirchhoff's current law is the direct consequence of conservation of charge.
Oh, and by conservation of charge, do you mean the total number of charges entering the junction should also leave the junction?
That's spot on. For instance, if 10 to the power of 5 electrons enter any junction, the same number of electrons must also exit the junction.
That sounds reasonable to me.
Since current is just the rate of flow of charge, current too, as stated by Kirchhoff's first law, gets conserved at that junction. You can take a simple analogy of 3 pipes, where 2 pipes are carrying water to the junction, while the third pipe is taking water away from it.
And the flow rate of the third pipe should be equal to the sum of flow rate of the first and second pipe.
Exactly.
Wow, that was a beautiful analogy, teacher. It clarifies the concept very well.
I agree. Moving on, do you know the expression of combined or effective or total resistance of 2 or more resistors connected in parallel?
You mean 1 over R is equal to 1 over R1 plus 1 over R2 and so on? I recall we have already learned how to use them in our previous grade, but why are you asking it now?
Well, the Kirchhoff's current law can be used to actually derive the expression.
Oh, can you tell me how it's done?
Sure. For that, let's consider three resistors with a resistance R1, R2 and R3 connected in a parallel as shown in the diagram here. So, can you apply Kirchhoff's current law at the junction or node A?
I think so. Here, the current entering the junction is I, while the current leaving the junction is I1 plus I2 plus I3. Hence, I should be equal to I1 plus I2 plus I3. Is that right?
Correct. Looks like you've got Kirchhoff's first law in the bag.
Of course. Anyway, what's next?
The process is simple now. From Ohm's law, we already know that I is equal to V divided by R. Also, since the voltage across each resistor is same in parallel combination, the currents mentioned earlier can be expressed as such.
That's easy to understand. Is substituting those values of currents in the earlier equation the next step?
Indeed. And that shall give us the required relation of combined resistance.
Oh, that's how it was derived.
Yes. Also, for your information, if there were only two resistors, R1 and R2, the early expression can be modified into a simple form, which is very handy to use.
Oh, I completely agree with you. By the looks of it, I can tell it's very handy.
It sure is. Since we have already derived the expression of combined resistance, what do you think happens if we add more resistors in parallel?
Give me a second here. The total resistance should keep on decreasing.
And why do you think that is the case?
That's because when resistors are connected in parallel, more current flows from the source than would flow for any of them individually. So the total resistance is lower.
You are right. Also, do remember that the combined resistance in a parallel combination is always smaller than the smallest individual resistance.
Finding this helpful? We have additional learning resources to offer. For Cambridge IGCSE and AS A-level subjects.
That was easy. We just need to apply Kirchhoff's first law.
Absolutely. Now that you're confident of Kirchhoff's first law, let's move on to his second law, also known as the loop law or voltage law.
Loop law, does that mean it can be applied in a loop or closed path only?
That's correct. It is the reason why it's also called a loop law after all.
Got it. So, what's its statement, teacher?
Kirchhoff's voltage law states that the algebraic sum of potential differences or change in potential in any loop must be zero.
I don't understand this at all.
I know. It seems rather confusing at first. Why don't we consider a simple circuit to have some insights?
Yes, let's do that. It would definitely be helpful.
Sure. Have a look here.
Two sources in the same circuit? This is the first time I'm seeing a circuit like this.
I know. But don't worry. There are some basic rules that make the analysis of such circuits easy.
Are there? What are the rules, teacher?
The first rule is we need to imagine the direction in which we will be moving around the loop of the circuit. That is either clockwise or anti-clockwise.
Does that mean we can choose to move in either direction?
You got it right. No matter whether we choose to move around the circuit in a clockwise or anti-clockwise direction, we will get the same result.
That's cool.
Right. So, which direction do you want me to move around in the circuit we have considered?
Let's choose anti-clockwise direction.
Sure. The second rule is we have to assume the direction of flow of current and indicate it by an arrow. Here too, we have total freedom to choose the direction.
Cool. In that case, let's assume our current is flowing in an anti-clockwise direction as well.
Let's do that then. With that, let's move on to the third rule. This rule is related to the sign convention of potential differences for the sources.
Okay. Is the sign convention of the source the rule which dictates whether the EMF should be taken as positive or negative?
Yep. It says that if the EMF is traversed from the negative terminal to positive terminal, the potential difference is taken as positive because we are moving from a region of low potential to high potential.
Got it. So, following the same line of thinking, if the EMF is traversed from the positive terminal to the negative terminal, the potential difference must be taken as negative, right?
Absolutely. You're definitely on the right track. Now, let's discuss the fourth or last rule. That is the sign convention of potential differences for resistors.
Sure. What's the rule?
The rule says that if the resistor is traversed in the same direction as the current, the potential difference is taken as negative. And the reason for this is we will be moving from a high potential region to a low potential region.
That's pretty straightforward.
Indeed. In a similar way, if we were to traverse the resistor in a direction opposite to the direction of current, the potential difference should be taken as positive, as shown here. Still with me so far?
I think so.
Don't worry. It'll be crystal clear once we start using the rules.
That's comforting.
Great. Now, let's get back to the circuit we considered before.
Does that mean we are actually going to apply Kirchhoff's second law now?
Yep. As suggested by you earlier, imagine you are moving in the anti-clockwise direction from point A in the loop, A, B, C, D, A. What's the first component you will come across?
It should definitely be resistor R1. Also, the potential difference here is I times R1, which should be taken as negative as the current direction is the same as the direction of the loop.
That's true. In a similar fashion, the potential difference across the next two consecutive components, R2 and R3, is I times R2 and I times R3 respectively, which are taken as negative 2.
That's understandable, as the current direction is the same as the direction of travel.
Exactly. Moving on, the next component we will come across is the EMF E2. Since we will be traversing this EMF from its negative terminal to positive, the potential difference should be plus E2.
Oh, I think I'm getting the hang of it.
That's good. In that case, please go ahead and find the potential difference across the last component in our loop, that is E1.
Sure. The potential difference across the cell E1 should be taken as positive, as we will be traversing the cell from its negative terminal to positive terminal.
Nicely done. Now, I'm sure that you have understood the sign conventions well. Getting back to Kirchhoff's second law, all in all, it says that the sum of all these potential differences in the loop A, B, C, D, A should be 0.
Oh, so that's what Kirchhoff's voltage law says, huh? It's definitely a challenging concept, but completely understandable.
I totally agree with you. One needs to practice a lot to get the grasp of it.
That's true. So, like before, I suspect there must be some quantity that is going to get conserved here, isn't it?
Exactly. Kirchhoff's voltage law is a direct consequence of conservation of energy.
Okay, but how? Can you connect the dots for me?
No worries. For that, let's consider a charge of 1 coulomb that is moving around the circuit. Whenever it moves through a source, it gains energy equal to the EMF of the source.
In that sense, whenever it encounters resistance, it loses energy that is equal to the potential difference across the resistance.
That's right. But if the charge ends up at the same point it started from, the energy gained and lost by the charge while moving around the circuit must be equal.
I see, but I'm still not sure about it.
Here's the thing. If the charge now has more energy than it previously had, it would mean that energy is created by the charge by simply moving around the circuit.
Isn't that impossible? We can't simply create energy out of thin air.
Indeed.
Ah, I get it now.
Register now for free.